A particle is often treated as the simplest thing physics can talk about. Something small, something localized, something that exists in a definite place and moves through space the way objects do at everyday scales. That assumption feels natural because much of classical physics is built on it. Careful measurement forced that assumption to be reconsidered. Particles did not behave like smaller versions of familiar objects. The more precisely their position was examined, the less their behavior matched the idea of a single, well-defined location. Attempts to track their motion stopped resembling continuous paths and started producing distributions instead. The description that worked in one experimental setup failed in another. That created a problem because physics depends on descriptions that hold across different situations. Instead of acting like tiny solid objects, particles produced statistical outcomes. They generated interference effects. They behaved as if multiple possibilities were involved before an interaction occurred, yet each interaction produced one specific result: a flash, a click, a mark on a detector. Something extended through space, something registered at a single location. Both features appeared in experiments. Removing either one broke the agreement between theory and observation. The meaning of particle had to change. A particle came to be treated as a repeatable physical event rather than a miniature object. It is defined by how it participates in interactions and how it shows up in measurements, not by a permanent shape or a fixed trajectory. It behaves consistently under the same conditions, even though its behavior cannot be reduced to ordinary motion. This explains why particles pass through matter without damage, why they can be created from energy, and why they can vanish in interactions without leaving pieces behind. Their behavior follows strict physical rules, but those rules are not the rules of solid objects. Space itself plays an active role. It carries physical properties and supports fields. These fields can be excited, and those excitations are what physics identifies as particles. Each particle corresponds to a specific kind of excitation with well-defined properties. This is why every electron is exactly identical to every other electron, not similar, exactly the same. They are not individual items with separate histories. They are the same physical occurrence appearing wherever the conditions allow it. Particles are not mysterious pieces of matter. They serve as the way the universe organizes interactions into discrete, countable events, rather than letting them dissolve into continuity. That perspective opens a deeper question, one that changes how existence itself is described. If particles are events rather than objects, what does it really mean for something to exist? To answer that, the safest move is to strip the word particle down as far as it will go and rebuild it carefully without relying on pictures borrowed from everyday life. At the most fundamental level known today, a particle is not a tiny object moving through empty space. It is a localized excitation of a physical field. That sentence sounds abstract, so let's slow it down and unpack it piece by piece. Physics describes the universe in terms of fields that exist everywhere. There is an electron field, a photon field, a quark field, and others. These fields are not things placed inside space. They are part of what space itself contains. They assign physical properties to every location, even when nothing dramatic seems to be happening there. Most of the time, these fields sit in their lowest possible state. Nothing noticeable occurs. But under the right conditions, a field can be excited. That excitation carries energy, momentum, and other properties. When such an excitation appears in a detector in a consistent, repeatable way, physics labels it a particle. So a particle is not something inside the field, it is something the field does. That distinction matters. It explains why particles are identical. Every electron carries the same charge and mass because each one is the same excitation of the same field. There is no manufacturing process, no variation, no individuality to account for. The field allows only one version of that excitation. It also explains why particles can be created and destroyed. When enough energy is supplied, a field can support an excitation. When that energy is removed or transferred, the excitation disappears. Nothing breaks. Nothing leaves fragments behind. The field simply returns to a lower energy state. This already contradicts a deeply rooted expectation that existence requires a permanent object. In modern physics, existence is tied to allowed activity within fields, not to enduring material pieces. Now let's look at motion. A particle is often imagined as traveling along a path, occupying one position after another, like a bead sliding on a wire. That picture works for baseballs and planets. It does not survive careful experiments at small scales. When physicists attempt to track a particle's position over time, the results do not trace out a single line. Instead, they form probability distributions. Predictions succeed only when the particle is treated as something spread out during its evolution, even though measurements always record a localized outcome. This is not a failure of instruments. It is not due to disturbance or lack of skill. It reflects how excitations of fields behave. Between interactions, the excitation is described by a mathematical object that encodes all the possible ways it could appear if measured. That description evolves smoothly and predictably. When an interaction occurs, one specific outcome is recorded. The rules governing both stages are precise and well tested. Trying to force this behavior into the picture of a tiny object following a hidden route leads to contradictions. Predictions fail. Experiments disagree. The idea of a particle as a small moving thing simply does not carry enough structure to describe what actually happens. This is where everyday reasoning runs into trouble. Everyday reasoning assumes that things have properties whether or not they are measured. It assumes position, motion, and identity exist independently of interaction. At small scales, those assumptions break down. Properties are not attached permanently to a particle. They are defined through interaction. A particle does not carry a position the way a coin carries a scratch. Position is something that appears when the particle interacts with something capable of registering location. The same applies to momentum, energy transfer, and other measurable quantities. That does not make particles vague or ill-defined. It makes them context-dependent in a precise way. This is why physics can calculate particle behavior with extraordinary accuracy while everyday descriptions fail. The calculations are built around fields, excitations, and interactions. The everyday pictures are not. There is another point that often causes confusion. Particles are sometimes described as waves. This does not mean a particle is a ripple in water or a vibration of matter. It means the mathematical description governing how a field excitation evolves resembles the equations used for waves. The similarity lies in structure, not substance. The wave-like aspects describe how possibilities spread and combine. The particle-like aspects describe how interactions register as discrete events. Both aspects refer to the same underlying entity. Refusing either description leads to errors. Keeping both leads to reliable predictions. At this stage, the concept of a particle should feel less like a thing and more like a rule-based occurrence. It is defined by the field it excites, the properties that excitation carries, the ways it can interact, the consistent manner in which those interactions appear. Nothing extra is added, nothing vague is required. Particles are how the universe packages interactions so that energy, momentum, and information move in discrete amounts rather than flowing without limit. They are countable not because someone decided to count them, but because the underlying fields allow only certain excitations and forbid others. This is why particle physics works so well. It does not rely on analogy, it relies on constraints. And that leads naturally to a deeper realization. If particles are excitations of fields, and fields fill all of space, then what appears solid, separate, and object-like at large scales is built from processes that are anything but. Matter is not assembled from tiny stones. It is assembled from permitted activity. That idea does not weaken the concept of a particle. It makes it strong enough to describe reality accurately. That conclusion places particles as expressions of a deeper physical structure rather than the final layer of description. Once fields take center stage, many puzzles that seemed disconnected begin to line up. Creation and disappearance of particles no longer feel dramatic. High-energy collisions in accelerators convert concentrated energy into new excitations. Detectors register them. Later, interactions transfer that energy elsewhere and the excitations fade. Nothing mysterious enters or leaves reality. The accounting remains exact because the fields never vanish. This perspective also explains why empty space refuses to behave like emptiness. Even in regions stripped of matter, fields remain present. They fluctuate. They carry structure. Those fluctuations influence measurable outcomes, from forces between objects to the stability of atoms. Space functions less like a container and more like an active participant. Another consequence follows directly. Particles possess properties only because the fields enforce them. Charge, mass, and spin arise from how an excitation couples to other fields. The values appear fixed because the rules allow no alternatives. Nature does not choose an electron's charge. The field permits only that option. Attempts to picture a particle as a tiny solid core quickly fall apart here. Solidity emerges only when enormous numbers of excitations lock together through electromagnetic interactions. At smaller scales, nothing behaves like a hard object. Interactions dominate. Resistance, rigidity, and contact emerge later as collective effects. This explains why particles pass through one another so easily. Two excitations can occupy the same region of space because fields overlap without obstruction. Interactions occur only when coupling rules allow them. Without coupling, nothing collides, nothing bounces, nothing blocks the way. The idea of location changes as well. A particle appears at a specific place when an interaction occurs that transfers energy locally. Between interactions, the excitation remains distributed according to strict mathematical rules. That distribution does not represent ignorance or lack of information. It represents the full physical description available. Here, everyday reasoning struggles, because everyday reasoning treats properties as permanent possessions. In particle physics, properties appear through interaction. Position arises when something records position. Momentum arises when something exchanges momentum. Energy transfer defines energy measurement. Remove the interaction and the property loses operational meaning. This does not weaken prediction, it strengthens it. Calculations based on field behavior predict outcomes with precision unmatched by any classical picture. Particle accelerators, semiconductor devices, and medical imaging all rely on this framework working exactly as described. Another common expectation fails at this point, the idea that smaller always means simpler. Particles appear small, yet their description requires layers of structure absent from larger objects. A rock follows simple equations because internal complexity averages out. A single excitation exposes the full machinery. This also clarifies why probability enters the story. The equations governing fields do not predict single outcomes, They predict distributions of outcomes. Each interaction selects one allowed result. Repeat the process many times, and the distribution emerges with remarkable consistency. Probability here reflects structure, not ignorance. The rules constrain outcomes so tightly that the statistical pattern remains fixed across experiments. Randomness appears only within boundaries that never shift. At this stage, the word particle serves a very specific role. It labels a unit of interaction that carries definite amounts of conserved quantities. Energy arrives in packets. Momentum transfers in packets. Charge exchanges in packets. Fields enforce this discreteness. Without particles, interactions would smear continuously. Energy would leak without limit. Stability would collapse. Atoms, chemistry, and matter would fail to form. Particles exist because the rules require discrete carriers. This also explains why particles feel countable. Counting does not impose discreteness. Discreteness allows counting. One excitation registers as one event. Two excitations register as two. No interpretation required. Even forces look different from this viewpoint. Forces describe how field values change across space. Particles respond by exchanging excitations. What feels like attraction or repulsion arises from permitted exchanges governed by symmetry and conservation. The language of particles survives because it remains useful. Detectors click, tracks appear, experiments record events. Talking about particles keeps communication efficient. But beneath that language lies the field-based structure doing the real work. This dual description causes confusion only when taken too literally. Treating particles as tiny objects leads to contradictions. Treating them as abstract mathematical ghosts misses their tangible effects. The field excitation view holds both sides together without strain. At larger scales, this picture fades into familiarity. Vast numbers of excitations interact, average out, and lock into stable arrangements. Tables resist pressure. Walls block motion. Objects occupy locations persistently. None of this contradicts particle physics. It emerges from it. Seen from far enough away, the details disappear. Seen closely, the machinery shows itself. Particles therefore occupy a precise conceptual role. They mark where and when interactions register. They carry conserved quantities between systems. They arise from fields and return to fields without residue. Nothing extra hides underneath. Nothing simpler waits beyond. That realization changes how matter, space, and interaction fit together. Reality does not consist of objects floating in emptiness. It consists of structured activity governed by rules that allow certain excitations and forbid others. Particles sit at the boundary between possibility and record. They translate continuous field behavior into discrete events that can be counted, measured, and compared. That role explains their strange behavior without reducing it. It also explains why attempts to force them into everyday categories repeatedly fail. The universe does not operate on familiar categories at small scales. It operates on permission and constraint. Particles simply follow those permissions with absolute consistency. At this stage, the picture is complete enough to use with confidence. Particles are not tiny, solid pieces hidden inside matter. They are localized excitations of fields that exist throughout space. Fields determine which excitations are allowed, which properties they carry, and how they interact. When an excitation transfers energy, momentum, or charge in a measurable way, physics records that event as a particle. This framework explains why particles are identical, why they can appear and disappear, why they pass through one another, and why interactions occur only under specific conditions. No extra ingredients are needed, no internal cores, no missing mechanisms. What physics knows with very high confidence is how particles behave, how they are produced, how they interact, and how their properties arise from fields and symmetries. These descriptions are tested continuously in particle accelerators, laboratories, electronic devices, and medical imaging systems. The agreement between prediction and measurement reaches levels of precision unmatched in other areas of science. Physics also knows that particles are not the final layer of description. They are effective representations of deeper structures. Fields underlie them. Symmetries restrict those fields. Conservation laws limit what can occur. This hierarchy is not philosophical preference. It is enforced by experimental results. What physics does not yet know is why the fields have the specific properties they do. It does not know why these fields exist instead of others, or why their strengths take the particular values measured. A complete framework that unifies all known fields at every scale has not yet been achieved. These limits are clearly recognized rather than hidden. That distinction matters. Physics is not uncertain about particles. It is precise about where certainty ends. From this perspective, matter is not assembled from rigid pieces stacked together. It arises from repeated interactions that remain stable because the rules allow them to. Solidity, shape, and persistence emerge from enormous numbers of excitations exchanging forces in tightly constrained ways. At larger scales, the details average out. At smaller scales, the underlying structure becomes visible. This also explains why the same particle language applies across very different situations. The electron in a wire, the electron in an atom, and the electron recorded by a detector are not different entities. They are the same excitation interacting within different environments. The surroundings change, the governing rules do not. The takeaway is direct and practical. Particles are how the universe makes interactions discrete. They are how conserved quantities move in finite amounts. They permit stability without locking everything in place, and variation without losing order. Without them, atoms would not hold together, chemistry would not operate, and matter would fail to persist. Thinking this way replaces the image of a universe built from tiny objects with one built from a loud activity. Nothing becomes vague, nothing loses precision. The description gains consistency across scales. When physics speaks about particles, it is not describing little things darting through empty space. It is describing how the underlying structure of reality registers interactions in countable, reliable ways. That perspective does not make the world harder to deal with. It makes the world workable.
I want to tell you something about learning that took me years to understand, even though I spent my whole life doing it. You see, most people think they're learning when they're really just collecting words. And I didn't realize how widespread this problem was until I went to Brazil to teach physics. Let me start from the beginning, though, because this story goes back further than that. When I was young, my father used to take me for walks in the woods near our home. He wasn't a scientist, he was in the uniform business, but he had this way of looking at the world that shaped everything I came to understand about real learning. One day, we were walking and he pointed at a bird. "You see that bird?" he said. "What kind of bird is that?" I didn't know. He told me, "It's a brown-throated thrush. In German, it's called a Halsenflügel. In Chinese, they call it something else entirely." You can know the name of that bird in every language in the world. And when you're finished, you'll know absolutely nothing about the bird. You'll only know something about people, what they call the bird in different places. He said, "Now, that bird, when it's pecking around in the leaves, it's looking for bugs. When it finds one, it eats it. The bird is converting energy from the bugs it eats into motion, into the beating of its heart, into the warmth of its body. That's what you should want to know." That conversation, it wasn't until much later that I understood what he was teaching me. He was showing me the difference between knowing the name of something and knowing something. And that difference, that simple distinction, is at the heart of everything wrong with how we approach learning. Let me tell you what I mean. I was asked to be on the curriculum committee for the state of California once to approve textbooks for schools. I was supposed to look through these books and decide which ones were suitable for teaching science. So I got this huge stack of books delivered to my house, and I started reading through them. And I noticed something strange. These books would say things like, "Energy makes things go," or they'd have pictures with captions, "This is energy." But they never explained what energy actually was or how it worked. They just gave it a name and moved on. One book showed a picture of a wind-up toy dog. The caption said, "What makes it move?" And the answer they wanted was energy. Now, think about this for a moment. A child looks at that toy dog and wonders what makes it move. That's a genuine question. That's curiosity. And what does the book tell them? It gives them a word, energy. But what have they learned? Nothing. They still don't know what makes the toy move. They've just learned to say a word in response to a question. They've learned to replace what makes it move with energy makes it move. That's not learning. That's vocabulary substitution. Real learning would be explaining that inside the toy there's a spring, and when you wind it up, you're twisting that spring tight, storing the work you're doing in the coiled metal. When you let it go, the spring uncoils, pushing against gears, making them turn, moving the legs. That's understanding. That's learning. But that's not what most education does. Most education teaches you to give the right answers without understanding what the answers mean. I really started to see this clearly when I spent a year teaching in Brazil. I was invited to teach physics at the Brazilian Center for Physical Research in Rio de Janeiro. I was excited about it. I thought I'd be helping develop physics education in a country that was building up its scientific infrastructure. But something very strange happened there. I would teach my classes, and the students seemed attentive. They took notes. They did the homework. But when I asked them to apply what they'd learned to a slightly different situation, not even a difficult one, just slightly different, they couldn't do it. They were completely lost. At first, I thought maybe I was a bad teacher. Maybe I wasn't explaining things clearly. So I tried different approaches, different examples. Nothing changed. Then I sat in on some other classes to see how the Brazilian professors taught. And I noticed that students were memorizing everything, not understanding memorizing. They could recite the definitions of things perfectly. They knew all the equations. If you asked them, what is Brewster's angle? They could tell you the exact definition from the textbook. But if you asked them a simple question like, when you look at water through polarized sunglasses and tilt your head, does the reflection you see change? They had no idea. They couldn't connect the concept of polarization, which they had memorized the definition of, to an actual physical phenomenon they could observe with their own eyes. I gave them an exam once with a question about a rotating wheel and what happens to its angular momentum. This was a standard problem, similar to ones we'd covered. Most of them got it wrong. But here's what was interesting. I looked at their work and I could see they were trying to apply formulas they'd memorized. They were plugging numbers into equations without understanding what those equations meant or why they worked. After class, I talked to some of the students. I asked them, don't you find this frustrating? Don't you want to understand this, not just memorize it? And one student said something I'll never forget. He said, but Professor, we have so much material to cover, there isn't time to understand it all. We just need to learn it for the exam. That hit me hard. Because he was right, in a way. The system had created a situation where understanding was actually a liability. Understanding takes time. Memorization is faster. If you have to get through a huge curriculum and pass standardized tests, memorization looks like the efficient choice. But it's not learning. It's the opposite of learning. At the end of the year, I gave a talk to the faculty and students about this. I told them that I'd noticed students could pass exams but couldn't apply what they'd supposedly learned. I suggested that maybe the problem was that they were teaching students to pass exams rather than teaching them to think. You know what happened? Some of the faculty got defensive. They said the students were learning what they needed to learn. They pointed to exam scores and graduation rates. But I'd seen the truth. These students could graduate with degrees in physics without being able to answer simple questions about the physical world around them. They had the vocabulary of physics, but they didn't have understanding. Now, you might think this is just a problem with the Brazilian education system in the 1,950 seconds. But I saw the same thing at MIT. I saw it at Caltech. I see it everywhere. Students come to me and say, I studied for hours and I still don't understand this. And when I ask them what they did during those hours, they tell me they read the chapter 3 times and highlighted the important parts. That's not studying. That's just moving your eyes across pages. Or they tell me they made flashcards with all the important equations. That's not learning physics. That's learning to recognize symbols. Here's what I learned about real learning. And this took me decades to fully understand, even though I've been doing it instinctively since I was young. Learning isn't about collecting information. It's about building understanding. And understanding, real understanding, means you can explain something in your own words, simply, without jargon. It means you can look at a situation you've never seen before and figure out what's happening using principles you've learned. It means you can see connections between ideas that seem unrelated. Let me give you an example from my own work. When I was at Los Alamos during the war, working on the Manhattan Project, we were dealing with incredibly complex problems. Nuclear fission, chain reactions, explosive lenses, these weren't things you could just memorize formulas for. The physics was new. Sometimes we were figuring things out that nobody had ever worked out before. There were people there who were brilliant, really brilliant. But I noticed something. The people who contributed the most weren't always the ones who knew the most facts or had read the most papers. They were the people who could think clearly from first principles. Hans Bethe was like this. He could work through a problem from the ground up, starting with basic physics, building up to the answer step by step. He didn't need to remember specialized formulas because he could derive what he needed from principles he truly understood. I tried to work the same way. When I didn't understand something, I wouldn't just look it up or ask someone for the answer. I'd work on it myself first. I'd draw pictures. I'd simplify it. I'd think about what was really happening physically, not just mathematically. Sometimes this was slower than just asking someone who knew the answer, but it built something in my mind, a way of thinking about problems, a toolkit of approaches I could use again and again. This is what I mean by real learning. You know, people sometimes ask me how I came up with the path integral formulation of quantum mechanics, or how I developed the diagrams that people now call Feynman diagrams. They act like these things came from some flash of genius, but they didn't. They came from trying to really understand what was going on in quantum electrodynamics. The existing formulations worked, you could calculate things with them, but I didn't feel like I understood them deeply. They felt complicated and abstract. So I asked myself, what's really happening? How can I think about this in a simpler way? I went back to basic principles. I thought about particles moving through space and time. I thought about all the possible paths a particle could take. I played with the ideas, drew pictures, tried different approaches, and eventually I found a way of looking at it that made sense to me. It was simpler, more intuitive, and it turned out to be useful for other people too. But here's the thing. I couldn't have done that if I just memorized the standard formulation and learned to calculate with it. I had to struggle with understanding it myself, in my own way. This is what education should be teaching, but it usually doesn't. Instead, we teach students to be passive recipients of information. We lecture at them. We give them textbooks to read. We test whether they can reproduce what we told them. But real learning is active. It's a struggle. It's trying to understand something, getting confused, working through the confusion, asking yourself questions, checking your understanding by explaining it to someone else or applying it to a new situation. I used to have this technique I'd use when I was trying to learn something new or solve a difficult problem. I'd imagine I was teaching it to someone who knew nothing about it. I'd talk out loud, explaining each step as simply as I could. And here's what I discovered. If I couldn't explain it simply, I didn't really understand it. The places where my explanation got confusing or where I had to use jargon, those were the places where my own understanding was weak. So I'd go back and work on those parts. I'd think about them differently. I'd look for simpler ways to say what was happening. And through this process of trying to explain it, I deepened my own understanding. This isn't just useful for teaching. It's useful for learning, because explaining something forces you to organize your thoughts. It shows you the gaps in your knowledge. It makes you think about the connections between ideas. I think if students spent less time reading and rereading textbooks and more time trying to explain what they'd learned to an imaginary person, they'd learn much more effectively. But our whole education system works against this. We reward students for getting the right answer, not for understanding how to get it. We give them problems that can be solved by pattern matching, recognizing that this problem is like that example. So you use the same technique. Real understanding means you can solve problems you've never seen before. It means you can adapt your knowledge to new situations. It means you can see when two things that look different are actually the same principle in different disguises. Let me tell you about something that happened to me at Caltech. I was teaching an undergraduate physics class, and I gave them a problem about a ball rolling down a slope. Standard problem, you can solve it with energy conservation or with forces and acceleration. One student came to me after class. She said, "I don't understand why we got the same answer both ways. Energy conservation and Newton's laws, aren't those different things?" And I realized she'd been taught to use both methods, but nobody had explained to her that they're not really different. Energy conservation is just a consequence of Newton's laws applied over time. They're the same physics, just looked at in different ways. She could use both methods to solve problems. She could get the right answers. But she didn't understand what she was doing. She was just following procedures. This is what most education produces. People who can follow procedures but don't understand the underlying reality. And the tragedy is that understanding is what makes learning valuable. Understanding is what lets you apply what you've learned to new situations. Understanding is what lets you see connections, have insights, create new ideas. Without understanding, all you have is a collection of facts and procedures that you'll forget as soon as you don't need them anymore. How much of what you learned in school do you remember now? Probably not much. But why? It's not because you have a bad memory. It's because you never really understood it in the first place. The things you truly understand, you don't forget. They become part of how you see the world. I'll tell you something else I noticed. The students who did best weren't always the ones who worked the hardest or studied the most hours. They were the ones who asked themselves questions while they learned. Not questions like, will this be on the test? but questions like, why does this work this way? And what would happen if I change this? And how is this similar to something else I know? These students were having a conversation with the material. They were actively engaging with it, testing it, probing it. They weren't just receiving information, they were digesting it, making it their own. This is what I mean by real learning. It's not a passive process. You can't learn the way you watch television. You have to do something with the information. You have to wrestle with it. I think about my father and those walks in the woods. He wasn't just telling me facts about birds or trees or physics. He was teaching me how to look at things, how to ask questions, how to think about what I was seeing. When we'd see something, a ball rolling down a hill, or water forming droplets on a leaf, he'd ask me, why do you think it does that? And I'd have to think about it. I'd have to use what I knew to try to figure it out. Sometimes I was wrong. That was okay. The point wasn't to always be right. The point was to think. That's real learning. Not knowing all the answers, but knowing how to think about questions. Not having all the information, but knowing how to understand new information when you encounter it. You know, people sometimes say to me, you're a genius. You understand things other people don't. But I don't think that's true. I think I just learned how to learn. I learned to not be satisfied with surface answers. I learned to keep asking why and how until I really understood. I learned that it's okay to be confused, as long as you work through the confusion instead of just memorizing something to cover it up. And anyone can do this. You don't need to be specially gifted. You just need to change your approach. Stop trying to memorize. Start trying to understand. When you read something, don't just read it. Ask yourself, can I explain this in my own words? Can I give an example? Can I see how it connects to something else I know? When you encounter a concept you don't understand, don't just move on or accept that it's too complicated. Stop. Break it down. What are the simple pieces? What's really happening here? When you think you understand something, test yourself. Try to explain it to someone else. Try to solve a problem you haven't seen before. If you can't, you don't really understand it yet, and that's valuable information. Now you know what you need to work on. This is harder than memorizing. It takes more time, more effort, more struggle, but it's the only way to actually learn. And here's what I've found. Once you start learning this way, it becomes easier, because real understanding builds on itself. When you truly understand something, it connects to other things you understand. You start seeing patterns, relationships, principles that apply across different areas. Memorized facts just sit there, isolated, waiting to be forgotten. Understanding becomes part of how you think. I'm an old man now, and I've spent my whole life learning. And the thing that still amazes me is how much there is to understand. Every time I think I understand something, I find a deeper level, a new way of looking at it. That's what real learning gives you. Not a collection of facts, but a way of seeing the world. Not answers, but the ability to find answers. Not knowledge that gets outdated, but understanding that deepens over time. The students I've taught who've gone on to do remarkable things, they're not necessarily the ones who got the best grades. They're the ones who learned how to learn. They're the ones who weren't satisfied with surface understanding, who kept asking questions, who wanted to know not just what, but why and how. And that's what I want to leave you with. Whatever you're trying to learn, whether it's physics or history or how to play an instrument or how to understand yourself, don't just collect information. Build understanding. Be patient with confusion. Work through it. Ask questions. Explain things in your own words. Look for connections. Test your understanding. Real learning is hard. It's supposed to be hard. If it feels easy, you're probably not doing it. You're probably just memorizing. But it's worth it, because real understanding is permanent. It's useful. It's beautiful. And it changes not just what you know, but how you think. That's what no one tells you about real learning. It's not about the information you put in your head. It's about changing your head, how it works, how it sees, how it thinks. That's the only learning worth doing.
Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic. But essentially, you picture a vacuum. You think of space as a stage, a big empty box where stuff happened. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of Jell-O sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that Jell-O, and I pull it. The Jell-O distorts. It stretches. If you want to describe what happened to that block, you can't just say, it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little, the far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that Jell-O, we need to know how much it stretched sideways, how much it stretched upwards, and how much it stretched forward. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of Jell-O is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a concept called a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about Jell-O. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have what we call a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly. It changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine. That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there. It flows from the hot spots to the cold spots. So, superimposed over your map of temperature numbers, there is a map of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it del, which is just a fancy name for a symbol that acts like a meat grinder for functions. You feed it the map of temperatures, and it chews it up and spits out a map of arrows. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature tells you the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a field of arrows that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you dropped a leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it.
Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Translation, electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. Translation, there are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the force on a moving charge. We call it the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place, and a sea of negative electrons flowing through them like a river. This is the current. Now, imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay? The magnetic field pushes the moving charge toward the wire. Simple. But wait. Let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So, if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it?
Einstein steps in. You see, when things move, space itself contracts. It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in, it's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So, what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector fields. We said earlier that fields define the force on a charge. We have an electric field vector and a magnetic field vector. What we just discovered is that these aren't two different actors. They are the same actor changing costumes depending on how fast you run past the stage. If you stand still, you see electricity. If you run, you see a mix of electricity and magnetism. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the conservation of charge. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal.
the electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, the divergence of the magnetic field is zero. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is something called the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboards. Because it turns out the magnetic field might just be a shadow of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to actually predict what the universe will do next, if we want to see the machinery under the floorboards, we need to talk about the ghost. We need to talk about A. In the simple world of electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple, intuitive. But magnetism is a headache. It doesn't act like a hill. It acts like a whirlpool. It swirls. So we can't represent it with a simple scalar number like height. We need something with direction. We need a vector potential. We call it A. Think of A as the momentum of space itself. Imagine a river. The water is flowing. That flow is A. If you drop a leaf in the river, it moves with the flow. But if you stick a paddle wheel in the river, it spins. That spin, that's the magnetic field. The magnetic field B is just the turbulence that happens around the edges of the flow of A. For a long time, physicists thought A was fake. They thought it was just a bookkeeping trick, a mathematical shortcut to calculate the real magnetic field. But then quantum mechanics came along and ruined the party. It turns out you can shield a particle from the magnetic field completely, hide it behind a lead wall where the magnetic field is zero, and the particle still feels something. It feels the river of A flowing past the wall. The ghost is real. In fact, the ghost is more fundamental than the thing it haunts. The vector potential is the primary fabric of electromagnetism. The magnetic field is just its derivative. Now I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds hanging in the void. But to truly understand the vacuum, you need to stop thinking of it as a cloud. You need to think of it as a solid object. You need to go back to the jello. When engineers study solid materials, steel, concrete, rubber, they use a branch of physics called elasticity. And when we study the vacuum of empty space, we find the exact same mathematics. Consider that glob of jello we talked about. Suppose you twist it and squash it. To describe the internal torture of that jello, you can't just say it's under pressure. Pressure is too simple. It pushes everywhere equally. But in a solid, you can push on one face while pulling on another. You can twist the top while holding the bottom still. We describe this internal mess with a stress tensor. Don't let the words scare you. A tensor is just a box of numbers. If a vector is an arrow, a tensor is a machine that takes an arrow and twists it. The stress tensor tells you exactly how much force is acting on every possible surface inside the material. It tells you, on the top face, we are pushing right. On the side face, we are pulling down. And how does the material respond to this stress? It deforms. We call this strain. If a tiny speck of dust inside the jello moves from point A to point B, that's displacement. But strain is subtler. Strain measures how the neighbors of that speck moved relative to it. Did they get closer? Did they drift apart? Did they rotate around it? This is defined by the strain tensor. It's the map of the distortion. Why am I talking about engineering concepts in a script about the universe? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on a very simple rule: stress times strain. How hard you push multiplied by how much it moves. This is true for a rubber band, and it is true for the vacuum of space. An electric field is a stress. A magnetic field is a strain. The empty space between the stars is loaded with potential energy. Stored in the electromagnetic fields exactly like elastic potential energy is stored in a twisted steel beam. This is why light exists. If you kick a block of steel, a wave travels through it. We call it sound. The speed of that sound depends on two things: how stiff the material is, how hard it fights back, and how heavy it is, how hard it is to move. If you kick the vacuum, a wave travels through it. We call it light. And the speed of light? It is determined by the stiffness of the vacuum and the density of the vacuum.
You have probably seen the constants epsilon 0 and mu 0 in physics textbooks. They look like boring numbers. They are not. They are the elastic constants of the vacuum. One tells you how hard space fights back against electric stress, stiffness, and the other tells you how much magnetic inertia it has, density. Light travels at c, not because it's a cosmic speed limit imposed by the police, but because that is the speed of sound in the solid block of nothingness we call the universe. But here is where the analogy gets really fun. Real materials aren't perfect. If you pull a spring too hard, it snaps. Take a piece of blackboard chalk. If you hold the ends and pull, it snaps in half. If you look at the break, it's a clean, flat cut, perpendicular to the pull. Why? Because chalk is brittle. It is weak in tension. It cannot handle being pulled apart. But now, take another piece of chalk and twist it. It doesn't snap straight across. It breaks in a spiral at a 45-degree angle. It looks like a corkscrew. Why? You didn't pull it, you twisted it. You applied a shear. But the math of tensors reveals a secret. A shear is just a tension in disguise. When you twist the chalk, you are actually creating a line of maximum tension running at 45 degrees along the surface. The chalk finds this hidden tension and snaps exactly along that line. Nature is full of these hidden mechanisms. The geometry of the stress dictates the geometry of the failure. Does the vacuum of space have a breaking point? Can you pull on the electric field so hard that space itself snaps? In classical physics, no. But in quantum electrodynamics, yes. If you create an electric field strong enough, a critical field, you can literally rip particles out of the vacuum. You can tear the nothing apart and create electrons and positrons out of pure stress. The vacuum isn't just a stage. It's a material that can be stressed until it breaks into matter. So, let's revisit our opening question. What exists between the object? The answer is everything. The quantum vacuum is not empty space. It is a plenum. It is a solid medium. It is a playground of fields described by vectors, scalars, and tensors. It has a temperature. It has a flow. It has stiffness. It has inertia. It has momentum. It can be twisted, sheared, and stressed. It stores energy. It carries waves. Understanding physics isn't about memorizing that gravity pulls or magnets attract. It's about learning to see the invisible scaffolding. It's about realizing that a differential equation isn't just algebra. It's a set of instructions for how the jello wobbles from 1 millimeter to the next.
Einstein didn't invent a new language to describe gravity. He just borrowed the language of geology and structural engineering. He looked at the universe and realized that space-time is just a giant, bendable solid, and gravity is just the strain tensor of the cosmos. So, the next time you look at the night sky, don't see emptiness, don't see a void, see the fields, see the tensors stretching and squeezing in the dark, see the huge invisible river of vector potential swirling around every wire and every atom. The universe is a crowded place, and the nothing is the heaviest thing in it.
Time doesn't exist, at least not the way you think it does. Not as this universal clock ticking the same for everyone. That's an illusion. And once you understand why, you'll never look at your watch the same way again. Every clock on Earth is lying to you. The one on your wall, the one on your wrist. And I don't mean they're broken or poorly calibrated. I mean something much more disturbing. There is no such thing as the correct time. Now you might be thinking, wait a minute, that's ridiculous. We all agree what time it is. Noon is noon. Midnight is midnight. We synchronize our clocks and they all say the same thing. And yeah, sure, for everyday life that works well enough. But here's the thing. It only works because we're all moving slowly. Very, very slowly compared to light. And we're all sitting in roughly the same gravitational field. The moment you change either of those conditions, your clock starts lying to you. Or more accurately, you realize it was never telling you the time. It was only telling you its time. Here's the secret. Time is personal. Time is local. Your clock measures your time. My clock measures my time. And these two times are not necessarily the same. So, let me explain what I mean by that. Because this isn't philosophy. This isn't some abstract idea you can argue about. This is measured. This is tested. This is real. Imagine you have two identical clocks. Perfect clocks. The best clocks anyone could ever build. You synchronize them perfectly. They tick together. They agree completely. Now you take one of those clocks and you put it on an airplane. You fly it around the world. And then you bring it back and compare it to the clock that stayed on the ground. They don't agree anymore. The clock that flew is behind. It's ticked fewer times. It's measured less time. And this isn't because the airplane vibrations messed it up, or because the pressure was different, or any mechanical explanation like that. No. Time itself passed more slowly for the moving clock. Now watch. This was actually done. In 1971, scientists put atomic clocks on airplanes, flew them around the world in both directions, and compared them to clocks on the ground. The results matched the predictions exactly. Time runs differently depending on how you're moving. But wait, there's more. It's not just motion that affects time, gravity does too. A clock at the top of a tall building runs faster than a clock at the bottom. Not by much, we're talking billionths of a second. But it's real, it's measurable. The clock closer to the Earth, deeper in the gravitational field, ticks slower. So what does this mean? It means time isn't this universal thing flowing at the same rate everywhere. Time is flexible. Time is stretchable. Time is, well, personal. And this leads to something even stranger. The concept of now itself becomes meaningless. The twist, think about it. When you say right now, you're assuming there's some universal moment that applies everywhere. That right now, as you're listening to this, there's also a right now on Mars, a right now in the Andromeda galaxy, a simultaneous moment across the entire universe. If you're standing still on Earth, you have one definition of now. If you're flying past Earth at high speed, you have a different definition. Events that are simultaneous for you are not simultaneous for the moving person. And neither of you is more right than the other. This is hard to accept, I know. We grew up thinking of time as this absolute thing, this river flowing at the same rate everywhere, this background against which events happen. But nature doesn't care about what we grew up thinking. Nature does what nature does. And what nature does is far stranger than our intuitions. Here's why this matters. For most of human history, we thought space and time were completely separate things. Space was the stage. Time was the clock on the wall. They had nothing to do with each other. Then along came relativity and showed us that's completely wrong. Space and time are not separate. They're woven together into a single fabric. We call it space-time. And everything that happens in the universe happens in space-time. You cannot talk about where something is without also talking about when it is. They're part of the same measurement, part of the same reality. So let me give you an analogy. Imagine you're looking at a map. On this map, there's north-south and there's east-west, two different directions, perpendicular to each other. Now imagine two people standing in the same spot, but facing different directions. One person faces exactly north. For him, north and east are clearly different directions, no confusion. But then the other person faces northeast. For him, what he calls forward is partly north and partly east. His forward is a mixture of the first person's north and east. Neither person is wrong, they're just using different reference frames. What's purely north to one person is partly forward and partly sideways to another. Space and time work the same way. What looks like pure time to someone standing still looks like a mixture of time and space to someone moving. They're not separate things. They're different directions in space-time. And how you divide them up depends on your motion. That's the key. When you move through space, you're also affecting how you move through time. There's a trade-off. The faster you move through space, the slower you move through time. And this isn't a metaphor. This is literally what happens. Everything moves through space-time at the same total speed. Always. You can't avoid it. When you're sitting still, not moving through space at all of your motion through space-time is directed through time. Time flows at its maximum rate for you. But when you start moving through space, some of your space-time motion gets redirected. Less of it goes through time. So time slows down for you compared to someone who's standing still. Now you might ask, okay, but if time slows down when I move, why don't I notice it? And that's a great question. The answer is because everything slows down together. Your clock slows down. Your heartbeat slows down. Your thoughts slow down. Every process that could possibly measure time slows down by exactly the same amount. So from your perspective, everything feels normal. It's only when you compare your experience to someone else's, someone who is moving differently, that the difference shows up. Your clock and their clock no longer agree. Your time and their time have diverged. And here's the shock. This isn't a small effect at high speeds. If you could travel at 99% the speed of light, time would slow down by a factor of about 7. 1 year for you would be 7 years for people back on Earth. Get even closer to light speed, 99.9%, and the factor becomes about 22. You could take a trip for a few years, come back, and centuries could have passed on Earth. You could outlive everyone you know. You could see the far future, not by living longer, but by having time pass more slowly for you while the rest of the universe ages. This is real. This is how the universe works. Time is not what you thought it was. Well, nature doesn't think in terms of space and time separately. Nature thinks in terms of space-time. And once you start thinking that way too, everything starts to make sense. Imagine you're driving your car on a road. The road goes north. You can measure how far north you've gone. Simple enough. But now the road curves. It starts going a little bit east as well as north. Now, for every mile you drive, you're not going a full mile north anymore. Some of your motion is being spent going east. The total distance you travel along the road stays the same. But how that distance gets divided between north and east, that changes depending on the direction of the road. Here's the truth. Space-time works exactly like this. There's a kind of distance in space-time, and everything travels through space-time. But how that travel gets divided between space and time depends on your motion. When you sit still, all your travel through space-time goes through time. You're not moving through space, so you move through time at the maximum rate. When you start moving through space, some of your space-time travel gets redirected into space. Less of it goes through time, so you age slower. Your clocks tick slower. Time dilates. It's not magic, it's geometry. It's the geometry of space-time. Now, this might sound abstract, so let me make it more concrete. There's a quantity in space-time that everyone agrees on. No matter how fast you're moving, no matter where you are, this quantity is the same. We call it the space-time interval. Think of it this way. In regular space, if I measure the distance between 2 points, I might get a different answer than you
if we're using different coordinate systems? Maybe I'm measuring in one direction and you're measuring in another. We disagree about how far east something is, or how far north. But the actual distance between the points, the straight line distance, that's the same for everyone. It doesn't matter how you orient your rulers. The distance is the distance. The key insight, space-time has something similar. There's an interval between two events, not just 2 points in space, but 2 events in space-time, meaning 2 locations that also have times attached to them. This interval combines both the spatial separation and the time separation. And just like the distance in regular space, this interval is the same for everyone. You might disagree about how much of it is space and how much is time, but the total interval, that's invariant. That's a fact of nature that doesn't change based on your perspective. So, when we say space and time are the same thing, we don't mean they're identical. Obviously, time feels different from space. You can walk backwards in space, but you can't walk backwards in time. There are differences. What we mean is that they're connected. They're part of the same geometric structure. You can trade one for the other, depending on how you're moving. But the underlying structure, the space-time itself, that's absolute. That's real. That's what nature actually cares about. But wait, we've been talking about motion. But what about gravity? How does gravity fit into all this? And this is where things get really interesting. See, for a long time, people thought of gravity as a force. You know, the earth pulls on you, you pull on the earth. There's this invisible rope connecting everything with mass. And for most purposes, that works fine. You can calculate orbits, predict falling objects, send rockets to the moon. But that picture is incomplete. It doesn't explain why gravity affects time. It doesn't explain why clocks at different heights run at different rates. Something deeper is going on. Here's what's really happening. Mass curves space-time. The Earth doesn't reach out and grab you with some invisible force. Instead, the Earth bends the space-time around it. And you, moving through that curved space-time, follow the natural path, which happens to curve toward the Earth. You feel this as falling. But really, you're just moving in a straight line through curved space-time. It's the space-time itself that's bent. And here's the beautiful part. Because space-time includes time, when space-time is curved, time is curved too. Near a massive object where space-time is more curved, time runs slower. Not because some force is acting on your clocks, but because the very fabric of time is stretched. Really think about that for a moment. Time isn't just affected by gravity. Time is part of what gravity bends. You know, people often think of curved space and have trouble visualizing it. What does it mean for space to be curved? Curved into what? But actually, that's the wrong question. Space doesn't have to be curved into anything. The curvature is intrinsic. It's a property of the space itself. Let me give you an example. Imagine you're an ant living on the surface of a balloon. You can only move on the surface. You can't go up or down. You can only crawl along the balloon's skin. For you, the balloon's surface is the entire universe. It's two-dimensional, but it's curved. If you walk in what feels like a straight line, you'll eventually come back to where you started. The surface wraps around. Now, we standing outside can see that the balloon is curved in three-dimensional space. But you, the ant, can figure out the surface is curved without ever leaving it. You can do experiments. You can measure angles of triangles. You can notice that the rules of flat geometry don't quite work. The surface itself has curvature, and you can detect it from the inside. Now watch this. Our space-time is the same way. It's curved. We don't need to ask, curved into what? Because the curvature is detectable from within space-time itself. We measure it by watching how clocks run at different rates, how light bends near massive objects, how objects accelerate toward each other without any force pushing them. This isn't philosophy. This is physics. This is measurable. And here's where time comes back in. The curvature of space-time near Earth is mostly curvature of time, not space. Space itself is barely curved at all near Earth. But time is significantly curved. That's why clocks at different heights tick at different rates. That's why falling objects accelerate. The time curvature is the dominant effect. So, when you drop a ball and watch it fall, what's really happening? The ball is moving through curved space-time. It's following the straightest possible path, what we call a geodesic, through that curved geometry. And because time runs slower closer to the Earth, that path curves downward. You think gravity is pulling the ball, but actually, the ball is just moving naturally through curved space-time. There's no force, just geometry. The twist here, this explains something that puzzled physicists for centuries. Why does gravity affect all objects the same way? A feather and a hammer in a vacuum fall at exactly the same rate. Why? If gravity were a force, you'd expect heavier things to feel a stronger pull. But they also have more inertia, more resistance to acceleration. These two effects exactly cancel. It seems like a coincidence, a very precise, very suspicious coincidence. But in the space-time picture, it's not a coincidence at all. Objects aren't being pulled, they're just moving through curved space-time. And the path through curved space-time doesn't depend on what the object is made of or how heavy it is. The geometry is the geometry. Everything follows the same curves. This is profound. Gravity isn't a force. Gravity is the shape of space-time. And time is part of that shape. So when I say time doesn't exist, what I mean is that time as this separate, independent, universal thing doesn't exist. Time as a river flowing at the same rate everywhere doesn't exist. That's an illusion created by our slow speeds and weak gravitational fields. What exists is space-time, this unified four-dimensional fabric that can be curved, stretched, and warped by the presence of mass and energy. Time is woven into this fabric, inseparable from space, relative to motion, affected by gravity. Your clock doesn't measure the time. Your clock measures its own journey through space-time. Nothing more, nothing less. And that's the truth. But if time is so flexible, if it's different for different observers, what's actually real? Is anything real? Or is everything just perspective? And this is where it gets beautiful. Because yes, some things are real. Absolutely, unchangeably, observer independently real. They're just not what you expected. The space-time interval between two events, that's real. Everyone agrees on it. The laws of physics themselves, those are real. They work the same way for everyone, no matter how fast they're moving. The speed of light, that's real. It's the same in all directions, for all observers, always. Here's the secret. What's relative is how you slice up space-time into space and time. That's a choice. That depends on your motion. But the space-time itself, the underlying four-dimensional geometry, that's absolute. It's like, imagine a loaf of bread. You can slice it straight across, or you can slice it at an angle. Different slices, different shapes. But the loaf itself doesn't change. The bread is the bread. Space-time is the loaf. Your now, your simultaneous moment across the universe, that's just one slice. Someone moving differently makes a different slice. But the loaf itself, the totality of all events in space-time, that's the same for everyone. So reality exists. It's just more subtle than we thought, more geometric, more unified. And now comes the shock. This picture of space-time, this four-dimensional block of reality, it has a disturbing implication. If the past and future are just different regions of space-time, and space-time is real, then in some sense, the past and future are just as real as the present. Think about it. The year 1800 exists in space-time. So does the year 3000. They're not gone or not yet happened. They're just in different locations in the four-dimensional structure. Your experience of now, moving forward through time, that's something happening within space-time, not something happening to space-time. Physicists call this the block universe view. All of time exists simultaneously, laid out like a landscape. We experience moving through it moment by moment, but the landscape itself just is. Now, I'm not saying this is definitely true. There are debates about this. Philosophers argue, physicists argue. It's not settled. But what is settled is that our naive view of time is wrong. The common sense idea that the present is special, that the past is gone, that the future doesn't exist yet, This view is incompatible with what we know about space-time. Something stranger is going on. We just don't fully understand what. But wait, there's more. Let's talk about something practical, something that shows this isn't just abstract philosophy. You've probably heard of those incredibly precise clocks, atomic clocks. They use the vibrations of atoms to keep time. They're so accurate that they would only lose or gain 1 second over millions of years. These clocks are sensitive enough to detect the time dilation from gravity, even just from being a few feet higher or lower. Scientists have measured this. A clock on a table runs at a slightly different rate than a clock on the floor. The difference is tiny, fractions of a billionth of a second, but it's there. So, what does this mean for your life? Well, technically, your head is aging faster than your feet, because your head is farther from the center of the Earth in a slightly weaker gravitational field. Time runs slightly faster there. Don't worry, the difference over an entire lifetime is about a billionth of a second. You won't notice, but it's real. Your head and your feet are in slightly different time zones. And it gets weirder. The atomic clocks used for navigation, these systems need to account for both effects. The clocks are moving fast, which slows time down, but they're also higher up, which speeds time up. The two effects work in opposite directions, and the engineers had to calculate both precisely to make the system work. If they ignored relativity, if they assumed time was absolute and universal, the system would fail within hours. Errors would accumulate. The whole thing would be useless. So this isn't abstract. This is engineering. This is practical. Relativity isn't just a theory. It's a fact that we rely on every day.
The truth is, we live in a relativistic universe. We always have. We just never noticed because we move slowly and live in weak gravity. Our intuitions evolved for the African savanna, not for high-speed travel or black holes. But now we know better. We've done the experiments, we've made the measurements, and the universe has told us in no uncertain terms that time is not what we thought. Now let me leave you with something to think about. We started by saying your clock is lying to you, and in a sense that's true. Your clock tells you its own personal time, not some universal time. It measures its own journey through space-time. But in another sense, maybe your clock is the only one telling the truth. It's telling you your time, the time you experience, the time that matters to your life, your aging, your existence. There's no cosmic clock in the sky keeping the real time. There's no universal present moment spreading across the cosmos. There's just space-time, and each of us traces our own path through it. When you really think about this, it's humbling. We walk around thinking we understand reality. We think time flows like a river, and space sits there empty and passive. We think our experience is how things actually are. But nature doesn't care about our expectations. Nature is deeper than we imagined, more connected, more geometric, more strange. And the beautiful part? We figured this out. Humans, on this tiny planet, orbiting an ordinary star in one galaxy among billions. We looked carefully at nature, did experiments, followed the logic, and discovered that space and time are woven together, that gravity bends space-time, that the universe is far more elegant and far weirder than anyone expected. That's the power of physics, not just collecting facts, but finding the hidden structure underneath, the simple principles that explain complicated phenomena, the deep truths that were always there, waiting to be discovered. Time doesn't exist the way you thought, but what does exist is more beautiful, more subtle, and more connected than anything we could have imagined. And we're still learning. We still don't have all the answers. Space-time near black holes, at the very beginning of the universe, at the smallest scales, there's still mystery there, still questions, still discoveries waiting to be made. That's what makes this exciting. That's what makes physics worth doing. We've learned so much, and there's still so much more to learn. So keep asking questions, keep being curious, keep looking at the world and wondering what's really going on. Because when you do that, when you refuse to accept easy answers and dig for the truth, you become part of this incredible tradition, this human tradition
of figuring out the universe, piece by piece, experiment by experiment, insight by insight. And who knows, maybe the next breakthrough will come from someone just like you.